Hello guys, what's up? So today we are going to discuss Open Book Quiz 6 on Chapter 3 of Form 4, Forces and Pressure. Okay, question number 1. We are given a cylinder, mass is 12 kilograms and cross-sectional area of 200 centimeters squared. What is the pressure acting at its base? Alright, so what do I know about pressure? Okay, so I do know that pressure equals to force over area. Okay, so in the questions, I do have the area. The area is given 200 centimeters square. Okay, but we don't work with centimeter, we work with meter. We are going to convert this into meter. And we are also given the mass, so we have the mass of 12 kilogram, but for a mass, okay, mass, it will have weight, right? So from W equals mg, okay, so I have 12 multiplied by 10, so the weight is 120 Newton. So this is our force, right? So I can now write my force 120 Newton. Okay, then my area. Okay, area is given 200 centimeter square. As I mentioned earlier, we don't work with a centimeter, so we are going to convert that into meter. So I have 200, okay, time centi is 10 to the power of -2, but our centi is being squared, so I have to put a square up here. So I only left with meter square. Okay, so do the calculation. You should be able to get 0.02 meter square. Okay, so the area is 0.02 meter square. Okay, so calculate the pressure. You should be able to get 6,000, okay, Newton per meter square. So this Newton per meter square, we have other name for it. That would be 6,000 Pascal. Alright, so that's how we calculate the pressure for question number 1. Remember that our force and area, okay, force and area, they must be perpendicular. So if the force is slanted, it's not perpendicular to the area, so you need to find the perpendicular force with respect to the area in contact. Alright, so we go to question number 2 now. Wind blows normally on a wall at the pressure of 200 kilopascal. The wall has an area of 5 square meter. What is the force acting on the wall? Okay, so notice the word here, normally. Okay, this normally means perpendicular. Okay, we have other terms, other word for it. We have orthogonal, also means perpendicular, right? That is just to enrich your English. Alright, so from the question we are given pressure. Pressure is 200 kilo Pascal. Okay, so that would be 200. Kilo is 10 to the power of 3 Pascal. So we have 2.0 times 10 to the power of 5 Pascal, correct? Alright, now area given in the questions is 5 square meter. Okay, so we want to find the force, right? So I do know that pressure equals force over area. Therefore, force equals to pressure multiplied by area. Okay, so substitutes the value of pressure 2 times 10 to the power of 5, and then the area is 5. Okay, then you should be able to get 1.0 times 10 to the power of 6 Newton. Okay, so we can also put this in terms of mega Newton, right? Because 10 to the power of 6, that would be mega. So it's 1 mega Newton. Okay, let's move on to question number 3 now. Alright, so question number 3, it shows a hydraulic jack. We have piston A, piston B. Okay, so the area of piston A, the area given here is 5 centimeter square, and B, the area is 100 centimeter square. Okay, and I have a mass of 3 kilogram, okay, on piston A. So mass is 3 kilogram, therefore the weight is equals to mg, right? So here I have 30 Newton. So I have a force pressing this smaller piston with a value of 30 Newton. And we want to find what is the maximum weight that can be lifted by piston B. Okay, so what is the weight here that can be lifted? So remember, our weight is actually our force. Okay, what do I know about this hydraulic jack? Okay, so I have liquids enclosed in this container. Okay, enclosed liquid, right? So the key word here, enclosed liquid. All right, so what do I know about pressure in enclosed liquid? The pressure is constant. Okay, so pressure must be the same throughout. So meaning to say that my pressure at point A here, okay, if I write this as my PA, pressure A, and here I have my pressure B, okay, so P, pressure A, must equal pressure at point B. Okay, who says this? Right, this is what is mentioned by Pascal. Okay, Pascal's principle. Okay, but pressure equal to force divided by area. Okay, so I have here force at region A, okay, piston A, divided by area at piston A. Oh my god, I have A there. Alright, equals to force at piston B over area at piston B. Okay, just a notation. Okay, force here on the smaller piston, piston A, I have force of 30 Newton. Okay, divided by 5. So in this case, you notice that I am not going to change my area into meter. Okay, because my area here is centi, here is also centi. They are consistent because we can cancel the centimeter square later on, so it's okay to leave it just like that. Okay, so I have force of 30, and then I have area of piston A is 5, equals to the force at piston B divided by the area is 100 centimeter squared. So calculate, okay, force at piston B. So if you do the calculation, you should be able to get 600 Newton. Okay, so here I have 600 Newton. So this is the maximum weight that can be lifted by piston B. Okay, if I input a force of 30 Newton on piston A, the maximum weight that can be lifted is 600 Newton. Okay, 600 Newton, meaning to say that the mass, okay, the mass of the load, the maximum mass, that will be 60 kilogram. All right, do you get it? All right, so in question 3, we are using Pascal principle, which simply states that the pressure at any points are equal. All right, so let's move on to question B. Now I have a ship. A mass 80,000 kilogram floats on the sea surface. Okay, so I have it floating on the sea surface. The density of the sea water is 1250 kilogram per cubic meter. And what is the volume of the displaced sea water? Okay, so I have a ship. Here is the surface of the water. Okay, and I have a ship. I have a ship here. All right, and the mass of this ship is 80,000 kilogram. So meaning I have a weight going down. Okay, here is W equals mg. That would be 80,000 multiplied by 10. That will give you 8.0 times 10 to the power of 5 Newton. Okay, so that is the weight of the ship. All right, and then at the same time, what do we have? I have a buoyant force. Buoyant force, it must be going up. And it says it floats on the sea surface. So meaning to say that my buoyant force must equal to my weight. Okay, so my buoyant force equals to 8.0 times 10 to the power of 5 Newton. Alright, what else do I know about this buoyant force? Buoyant force is also equal to the weight of, okay, the weight of liquid displaced. Who said this? Right, our remember? Our Archimedes. Alright, so Archimedes says that for a floating object, the buoyant force equal to the weight of the liquid displaced. Alright, now, how am I going to get the weight of the liquid displaced? In the questions, you are given the density, and you are to find what is the volume. Okay, so no big deal. From density equal to mass over volume, correct? All right, so how are we going to solve this? Okay, so I can also write my buoyant force, okay, equal to the weight of the liquid. So I'm going to put this as mg, yeah? So here is mg, mass of the liquid displaced multiplied by our gravitational acceleration, right? To get the weight. All right, so I need to know my m here so that I can put m here into this equation. So m equals to rho v, density multiplied by volume. So next I am going to substitute my m, my mass, into these equations of buoyant force equal to the weight of the displaced liquid equal to the weight of the ship. All right, so here rho v g, okay, m is rho v, So we just substitute it there. So I have rho V G equals 8.0 times 10 to the power of 5. Okay, my density is 1250 multiplied by the volume of the displaced seawater multiplied by the gravity, then okay, equals 8.0 times 10 to the power of 5. So here you only have one unknown, so that will be easy to calculate now. So the volume upon calculating, you should be able to get 64 cubic meter. All right, so that is the volume of the water displaced. So what have we been using here? Okay, here we are saying that the buoyant force equal to the weight of object. Okay, remember that this object is floating, it is not sinking, it is not going up, not going down, it just stay there floating. Okay, so at the same time, this equal to the weight of liquid displaced. Okay, so this is what we have been using in solving this question. Okay, try to understand how we work the question out. All right, done. So let's move to question number 5. Okay, now we have a metal tube and then we blow at the opening. So when we blow at the opening, so here the velocity of the air would be higher, right? So Bernoulli says that whenever we have high velocity, okay, high velocity, then the pressure must be low. All right, so at the opening here, the A movement, okay, it moved with a higher velocity, therefore at the opening here I have a regions of low pressure, but inside here I don't have any air movement. Okay, if there is, then it will be very slow, then the velocity at this region, okay, the velocity must be very low, hence the pressure must be high. Okay, this is what Bernoulli says. Oops. Okay, this is what Bernoulli say. Okay, the Bernoulli's principle. Okay, so at the opening the pressure is low, inside here the pressure is high, so we have a difference in pressure. So the difference in this pressure, okay, will give rise to a resultant force that will make the ball to be lifted up to the opening. Okay, so this resultant force is due to the difference in the pressure. Okay, so try to understand the concept there. Okay, so we are using Bernoulli's principle. Okay, let's move to question number 6. So now I have a my V. Okay, this my V, the mass is 900 kilogram, and then it is also mentioned that the air pressure for each tire is 2.0 times 10 to the power of 5 Pascal. Okay, for each tire, right? So the mass is 900 kilogram. Okay, and then the pressure is 2.0 times 10 to the power of 5 Pascal each tire. Okay, not the sum of all the tires, you will get this, but one tire is 2.0 times 10 to the power of 5. Okay, what is the meaning of pressure? Remember that our pressure equal force over area. So put this into words, then pressure is force per unit area. Simple, right? Okay. Even though it's not wrong to write it force divided by area, but make it a habit, okay, to write pressure as force per unit area. Okay, so let's go to question B. Calculate the area in contact with the ground for each tire. So we are going to use pressure equal to force over area, and we want to find what is the area. Okay, so remember up here we are given the mass is 900 kilogram, pressure of each tire is 2.0 times 10 to the power of 5 Pascal. So we are going to analyze this systematically. So we are going to assume that this mass 900 kilogram will be distributed equally. Okay, I repeat, the mass, okay, 900 kilogram, this will produce weight equals mg. The weight would be 9,000 newton. Okay, so this weight, it will be distributed equally among the 4 tire, meaning to say 9,000 divided by 4 tire. So every tire, okay, it will have its own amount. That will be about 2250, not mistaken. All right, so let's continue with the working here. All right, so the weight of the car equals mg. M is 900 kilogram, G is 10, so I have 9,000 Newton. Okay, so the weight on one tire, that will be 9,000 Newton divided by 4. Alright, so here you will get 2,250 Newton. Okay, so this is the weight to be withstand by one tire. So you have 4 tires, so the total weight, that will be 9,000 Newton. Okay, do you follow me? This is the weight that need to be withstand by one tire. So one tire will hold 2,250 Newton. Alright, so now I am going to plug that value into my pressure equation. P equal to F over A. Okay, so the pressure for one tire just now, it is given 2.0 times 10 to the power of 5. And then the force is given here. Remember that force is weight, weight is force. Alright, so here is 2250 divided by the area. Okay, the area of the tire in contact with the ground. So solve for A, you should be able to get 0.01125, and the unit here is meter square. Okay, don't trust my calculation. You need to verify my calculation. Make sure that it is 0.01125 square meter. All right. So let's go to C now. Madonna drives her car to her school with a distance of 10 kilometers, and she finds out that the car tires become harder. Okay, so the tire of the car becomes harder. So why it becomes harder? Something is pressing the wall of the tire outward, okay, making the tire to become harder. Okay, just now I used the word pressing, okay, so meaning to say I am inferring pressure. And then what causes pressure in the tire? It is the collisions of the air particles in the tire with the wall of the tire. All right, so the higher the collision, then the higher the pressure, I mean the rate of collision. But what is causing the collision, the rate of collision to increase? Well, it's due to the increase in the kinetic energy. But then what make our kinetic energy to increase? Well, increase in the temperature of the air inside the tire. Okay, so I am answering it backwards. All right, so we start with the temperature of air inside the tire increases, and this will cause the kinetic energy to increase. So when we have increase in the kinetic energy, then the rate of particles collision with the wall, it will be increased as well. So when the rate of collision increases, this in turn will cause the pressure to increase. And if the pressure is increased, therefore the tire will become harder. Okay, do you get that? All right, let's move to question number 7. Diagram shows a setup of apparatus for measuring atmospheric pressure. Okay, so up here I have vacuum. The distance here is 76 centimeter. Oops, here is mercury. Okay, so name the instrument above. So this is used to measure atmospheric pressure. Okay, so for atmospheric pressure, remember that we have a unit called bar. All right, so this instrument is called barometer. All right, so name the instrument. So this is a barometer, or you can also say simple barometer. Okay, next, determine the atmospheric pressure as measured by the instrument. So if I look at my diagram here, okay, it is measuring the atmospheric pressure, and the length of this mercury column is 76 centimeter. So what is my atmospheric pressure? So P atmospheric is 76 centimeter mercury. So that is the atmospheric pressure. So here is 76. So what is 76 centimeter mercury in Pascal? Okay, that will be 1.0 times 10 to the power of 5 Pascal. Alright. Now, let's go to C. State the change of length of the mercury column above if the tube is raised by 10 centimeter. Okay, if I lift this tube up, okay, if I lift this tube up, what will be the length of this mercury column? Is it going to be 76? Is it going to be increased? Well, remember that this instrument is to measure atmospheric pressure. Whatever you do to the length of this column, okay, of this tube, the length of this mercury column will remain the same vertically. Okay, if I slant this thing, if I tilt this at a degree, maybe 45 degree or 60 degree, the vertical length, okay, the vertical length of the mercury column, it remains 76 centimeter. Okay, mercury. So let's go down and answer the question. Okay, the tube is raised by 10 centimeter. So what happened to the length of the mercury column? Alright, here would be no change. It remains 76 centimeter. And what if the surrounding temperature increases? So what happened to the length of the mercury column? Okay, if the surrounding temperature increases, then this one here will increases. Meaning to say that the atmospheric pressure will increase. Alright? Why? Well, temperature increases. Then what comes next? Kinetic energy will increase. What comes next? Collision, correct, will increase. Okay, the rate of collision will increase. And what comes next? Pressure will increase. Alright, so the length of the mercury column will increase. Now, the instrument is brought to the peak of Mount Sentubong. So what happened? So on the peak of a mountain, okay, so we have less particles there, right? The air would be very thin. So meaning to say less particles. Do you get it? Less particles. Meaning what happened to the rate of collision? Decrease, right? So the rate of collision decrease, what happened to the pressure? Yes, so the pressure will decrease as well. So the answer here, if we are going to bring this instrument to the peak of Mount Sentubong, so the length of the column of mercury will decrease. Alright, next. If the vacuum region is replaced with water vapor. So if I go up here, initially I have vacuum. Vacuum, there is no air, there is no particles. No particles, then there will be no way for collision to occur. No collision, so what happened to the pressure? So the pressure, it must be approximately 0, right? So nothing is pressing the mercury going down. Okay, so nothing is pressing the mercury here to go down. But if I have something else here, take for example in the question it says replace this vacuum to water vapor. So what are we doing to the region here? We are adding particles. Now I have particles dancing around. So these particles will collide with the wall here and create pressure, right? So now I have pressure here. So what does this pressure do? It will push the mercury column downward. So what happened to the length of this mercury column? Yes, the length of this mercury column will be decreased. All right. So here the answer would be the decrease. Okay, so for this one we have answered it just now. There will be an change, no change. Okay, here we are talking about in terms of vertical length. All right, hope you can understand my explanation there. Okay, let's move to question 8 now. Here we have a vacuum cleaner. Okay, when the switch is on, okay, I spell it wrongly. Switch is on, the motor will rotate, the fan and the dust will be sucked in. Okay, so the fan will be rotating, and what happened? The dust will be sucked in. Okay, so this vacuum cleaner is a sucker. Okay, so what is the function of the fan? Okay, what does the fan do? The fan rotates. Okay, so when it rotates, what does it do? It will suck the air inside this compartment out. Okay, suck the air out. So what happened here? Partial vacuum. Okay, why? Because the particles of the air has been sucked out. So there will be very few particles left here. Hence, the rate of collision with the wall of this compartment will definitely be reduced significantly. Alright, since there is no collision, therefore no pressure. Okay, so the pressure here is almost zero. That's why we say it's partial vacuum. Okay, so that is the function of the fan, to suck the air out from the dust compartment to create a partial vacuum region in the compartment. Okay, B1, mark X on the diagram, which is the lower pressure area. So we have mentioned it just now. Here I have partial vacuum, so X is here. Okay, in this compartment. Not only in this compartment, here, okay, is also X. Here is X, here is X, here is X. Why I mark all this as X's? Because the fan, okay, it sucks the air out, not only from this dust compartment, but also in the hose here, being sucked out the air, okay, by the fan. So I have partial vacuum from the nozzle until my dust compartment. Okay, follow? Alright. Describe how the lower pressure area at X can be produced. So we have explained that earlier. So air is removed from area X, leaving very few particles staying there. Collisions of air particles with the wall of the compartment is reduced. Maybe we can add here the rate of collision of air particles with the wall of the compartment is reduced. Therefore, the air pressure is lowered as well. Okay. C. How does atmospheric pressure helps the working principle of a vacuum cleaner? So remember, at this point here, okay, at the nozzle here, my pressure is low. But outside here is the atmospheric pressure. So the atmospheric pressure is greater, is higher than the pressure inside this. So what happened? I have a difference in the pressure. Okay. So this will result in a resultant force that will push the dust from outside, okay, into the nozzle. Okay, because the pressure always act from high region to lower region. All right, that is the resultant force. All right. So to answer this question, we can write atmospheric pressure is greater than the pressure in region X. The difference in pressure creates a resultant force which pushes the dust into region X. That's how a vacuum cleaner works. Okay. Alright. Let's move to D. This boy is trying to suck the water out through a straw, but the straw I have a hole. Alright. So if I can enlarge the straw, okay, so here is down here is the water, maybe Coca-Cola. So I have P atmospheric here, right? Pressing the water here, the surface of the water, so that the water will go inside here, correct? Because inside the straw we're supposed to have lower pressure, right? But I have a hole here, so what happened? Okay, so I have P atmospheric also pressing here. Okay, it pressed downward. At the same time, I have P atmosphere here trying to push the water into the straw. But at the same time, this atmospheric pressure is going to push the water out from the straw. Alright, so why can't the boy suck the water into his mouth using the straw? Simple, it is because of the pressure inside the straw. Okay, pressure in the straw is equal to the atmospheric pressure. So as you can see here, there is no difference in the pressure. There's no difference in the pressure, meaning to say there will be no resultant force. Alright? So there's no way for the water to be sucked into the boy's mouth if there is a hole in the straw. Alright, so stop here first. We will continue later.